Bien, bonjour à tous. Je crois qu'on est maintenant au quorum, tous les jurys sont là, moi compris. Nous sommes là pour assister à la soutenance de thèse de Guillaume Dréau, le résultat de 3 ans de travail assez remarquable, je reconnais. Et le titre, tout d'abord, Guillaume va nous présenter son travail en 40-50 minutes. Ensuite, il y aura le temps pour les questions des membres du jury et des chercheurs de l'Assemblée, si il y a des questions à poser. Ensuite, nous nous retirerons pour délibérer et ensuite, nous présenterons les résultats de la délibération. Et il y aura aussi, tu devras prêter serment à la fin de la séance. Bien, donc, tu vas nous parler des études sismiques des géants trous sur la branche asymptotique. Et donc, tu as 40 à 50 minutes pour nous faire ta présentation. Merci.
Merci. So first, I would like to thank everyone for coming here and attending my presentation, and specifically for the members of the jury to be present here. And so I'm glad to present 3 years of work about the seismic analysis of red giants on the asymptotic giant branch, under the supervision of Benoît Mosser and Yves Breton. Thank you for suggesting me this subject, which was very impressive. So before going straight into the subject, the beginning of our journey on the evolution, stellar evolution, starts at the main sequence, where the hydrogen burns in the core. Once the hydrogen in the core is depleted, the star leaves the main sequence and ascends the subgiant branch, where restructuration is ongoing until the star reaches the bottom of the radiant branch. At this stage, the envelope expands and the core contracts, and the hydrogen burns in a shell. So because the envelope grows, the luminosity increases, so it climbs up the RGB, radiant branch, until the star reaches a point where the temperature is high enough in the core to burn the helium. So first, it happens in an unstable condition, and once the helium burns in a stable condition, the star reaches the clump phase, so the core helium burning phase. Once the helium is depleted, the star leaves the clump phase and begins the asymptotic giant branch. And on the early asymptotic giant branch, you can see a specific feature here, which is turning back of the evolutionary track that we refer to as the asymptotic giant branch. So the helium in this stage burns in a shell, and the luminosity increases as the envelope expands, and it reaches high luminosity stages. In this work, we mainly focus on the evolved stages of RGB and HB at high luminosity stages. And in the first part of this presentation, I will show you the results of performing a seismic analysis of evolved giants. And we will investigate the seismic signature of stellar evolution. In the second part, we will focus on a very specific region of the Hertzsprung-Russell diagram, so showing the luminosity as a function of the effective temperature, which is the asymptotic giant branch bump. We would like to study the dependence of the HGB bump with stellar parameters. And we would like to assess the potential of the HGB bump to constrain stellar models. So we start with the first part, so a global analysis of red giants, including RGB and HGB stars, especially the classification between the 2 evolutionary stages. So disentangling evolved HGB from evolved RGB stars is not straightforward, as you can see from an observational point of view, by looking at the color magnitude diagram in the high-band pass filter in the globular cluster M5, you can see that the RGB represented by triangles and HB represented by squares, that at high luminosity stages, they are close to each other. So disentangling them is not straightforward with the classical photometric quantities. If we look in stellar models, for example, in the one solar mass evolutionary track computed with MESA, we can see that those branches are very close to each other. So both from an observational and modeling arguments, this is not straightforward to disentangle both evolutionary stages. However, as you can see in the Kipenen diagrams showing the mass integrated from the center of the star as a function of the stellar age, there are clear structural differences. The extent of the convective envelope is not the same. There is a substantial mass loss that HB stars suffered, and there is an additional helium burning shear. So we would like to constrain these stellar interiors and using asteroseismology. So what is asteroseismology? It consists in probing stellar interiors with waves that propagate inside stars and which are sensitive to stellar evolution. In case of red giants, the main source of information is pressure waves. These pressure waves, as represented on the drawing here, are excited by the turbulent convection near the stellar surface. The constructive interferences between all the waves that are created by the turbulent convection will give rise to the stellar oscillations, which is represented here, for example, for a radial mode. It creates this small expansion and contraction, creates variations of luminosity, which can be highlighted in the light curves showing the luminosity flux as a function of the time. The oscillation modes can be highlighted by taking the Fourier transform, or more specifically, the Lamb-Skarloff transformation. And in the range of frequency of oscillations, we can highlight a bump in the power spectral density, which corresponds to the oscillation spectrum. So if we zoom in this specific part of the power spectral density, we can highlight a specific pattern in the oscillation spectrum of evolved giants. We can highlight at a given radial order and a pattern of 3 modes, which are the L equal 0, the radial modes, in red, the L equal 1 modes, the dipole modes in blue, and the quadrupole modes, L equal 2, in green. This pattern of 3 modes repeats at a given frequency interval named the large separation delta nu. And the maximum oscillation power is not, the frequency at maximum oscillation power is noted nu max. These modes, their frequencies can be represented by the asymptotic pattern of red giants, which has been established by Werner Molzer and his collaborators in 2011, which is recalled here, where several seismic parameters are present, such as the acoustic offset epsilon, the small frequency separation D0L, and the large frequency separation, which is also represented here. So basically, for these evolved stars that we analyze, the typical large separation will be at a value lower than 2 microhertz. These seismic parameters are very, very important because they can be used to build classification method between different evolutionary stages. This is, for example, what we can do with using the parameters delta nu and delta pi 1. So delta nu, which is the frequency difference between modes of consecutive radial order at a given degree L. So here specifically for L equals 0 modes, and delta pi 1, which is the same definition, but in terms of period for the dipole modes. Here you can see on the delta pi 1 delta nu diagram that you can distinguish shell hydrogen burning shell, so RGB, and a core helium burning shell, a core helium burning phase, and a shell helium burning phase. Here you see that RGB stars have lower delta pi 1 than their HB counterparts in a given range of delta nu, with the dispersion of the mass. This classification method is based on a clear different physical structure between those two evolutionary stages. So in case of the HB star, there is an additional helium burning shell, and for core helium burning stars, there is a convective core that is present for core helium burning stars that is not present for RGB stars, which makes these different values of delta pi 1 measurable between RGB and HB stars. However, as you can see, the classification method ends at delta nu equal to 3 microhertz. This is not mere coincidence, because the method is no longer applicable at low delta nu, because the modes that are used to compute delta pi 1, so the dipole modes, are no longer measurable on at low delta nu. So we need to rely on another classification method. For example, Thomas Kallinger and his collaborators in 2012 have highlighted a classification method based on the asymptotic pattern of radiance. So using the information from the pressure modes. Particularly, they used the acoustic offset epsilon and showed that the measures on the RGB are higher than that on the asymptotic German range. The issue with this classification method is that we cannot identify clearly the physical basis on which this classification method relies, simply because the physical sources contained in the epsilon, the acoustic offset, comes from different contribution from the near surface term. However, we can find the physical basis on which this classification relies. If we differentiate the asymptotic pattern of radiance, we can make the link between a small quantity of the acoustic offset and that in the local large separation. The difference that you would measure in delta nu would be equivalent to having a difference in the acoustic offset epsilon. And the works of Matura and his collaborators in 2015 have shown that the perturbation induced by the second helium ionization zone in the measurement of delta nu, which can be modeled by an oscillator model, have shown that the phase of this modulation varies between RGB stars and core helium burning stars, which induces perturbation to the measurement of delta nu, and they have shown that these perturbations are equivalent to that which are measured with the classification method of Thomas Kallinger and his collaborators. So this classification method relies on the signature of the second helium ionization zone. However, in this case, this has only been done for RGB stars and core helium burning stars. We still need to demonstrate it between RGB and HB stars, which is the first aim of this presentation. This will be done by characterizing able stars through their seismic signature in the oscillation spectrum. And we will investigate this observational signature in terms of structural differences between RGB and HB stars, which is the first aims of this part. So first, we need to extract the mode properties in the oscillation spectrum. This will be done with a specific sample of stars using Kepler targets. So it includes evolved RGB, clump, and HB stars, for which the delta nu, the large separation, is lower than 4 microns. So here you have the histogram of our sample of stars on the left, and on the right, you have the distribution of our stars in the Hertzsprung-Russell diagram. So here, instead of showing the luminosity, we show nu max in the ordinate axis, but this is equivalent to showing the inverse of the luminosity, because there is an inverse relation between nu max and the luminosity. So in blue, you have the Radian branch stars, in red, helium burning stars, and in gray, undefined evolutionary status. So in the sense that the evolutionary status is taken from the classification method done by Thomas Geiger, which relies on the acoustic offset, epsilon, and that in agreement with the classification method performed by Bernard Moser and his collaborators in 2019, which relies on the strength of the seismic signal. So with this sample of stars, we can extract the seismic parameters in the oscillation spectrum. So here you can see the oscillation spectrum of Radian branch stars at low delta nu, so that observed in black, and in blue we model a template oscillation spectrum which is based on the asymptotic pattern of red giants. So we take initial guesses for the seismic parameters, for the acoustic offset and a small separation, as a function of the scaling relation established in the work of Bernard Moser and his collaborators in 2011. And what we do is that we use a maximum correlation method to adjust the template oscillation spectrum on the observed oscillation spectrum. So that we compute the optimal value of delta nu, which maximizes the correlation between the two, and we extract a measurement of delta nu. This also gives us the identification on the modes of the modes in the oscillation spectrum, such as the degree and the radial order. Finally, all the peaks that you can see in the oscillation spectrum, we apply detection thresholds to verify if they are indeed detected stellar modes. So we use two criteria, one on the mode height, so the signal to noise ratio must be high enough, and the one criterion on the mode frequency. So in terms of frequency, the mode must not be too far from that we would expect from the asymptotic pattern of red giants. This method allows us to extract mode frequencies according to observations. But we want to do more. We want to interpret our results in terms of stellar structures. To this end, we compute stellar models with the stellar evolution code MESA. So from the early stages, from the main sequence, up to the high luminosity stages of the asymptotic giant branch. In these stellar models, we include physical parameters such as overshooting, which is the additional mixing region above the convective core. So it can be during the hydrogen or helium burning phase. And also, so the overshooting below the convective envelope. So with free parameter alpha overshoot, which is expressed in units of the pressure scale height. On top of that, we consider mass loss prescriptions. So the Reimers one on the right RGB and the blockers one on the HB. And we calibrate our models according to the sun. So our free parameters are the helium abundance, the metallicity, and the mixing length parameter, which represents the efficiency of convection in stellar interiors. So we calibrate these parameters such that the luminosity and the radius is reproduced at solar age. So this allows us to model the evolution from the main sequence up to the asymptotic giant branch. And with these stellar models, we can use them as an input to another stellar code, which is at 80 poles, which allow us to compute the mode frequencies associated with these stellar models. So we have a method to extract the mode frequencies in observations, and blues we would extract from stellar models. So we can start studying the signature left by the second ionization zone in mode frequencies. So what is the second helium ionization zone? So this is a sharp variation region of the first adiabatic exponent, which is reminded here as a function of the derivative of the pressure with respect to the density, over a short distance with respect to the wavelengths of the oscillations. So here you can see the profile of gamma 1 as a function of the acoustic radius, which represent the distance from the center of the star, but expressed in terms of time to travel at sound speed. The strength of the gamma variation is noted H helium-2. The size of the gamma 1 variation is noted delta helium-2, and the location in the acoustic radius is noted T helium-2. So what does this region imply? What are the effects of this region in the mode frequencies? Given that the asymptotic pattern does not take into account the effects of such region, we have to introduce another term in the mode frequencies, which is delta nu NL, and which is also called the glitch. So this is a small valid in case of a small perturbation to the asymptotic pattern of regions, and it can be extracted by comparing it with what we would expect from the asymptotic pattern of regions. In our case, because the modulation introduced by the second ionization zone is small, we won't directly extract it from the universal pattern of regions, which the leading order term is important. We will instead look at the local large separation. So here, the local large separation for which the effects of the glitch are present are that we measure the measurement we extract directly from the oscillation spectrum. And we compare it directly to what we would expect according to the asymptotic pattern of regions. So directly by computing it with the asymptotic pattern of regions. By computing the difference between the two, we are able to extract the signature of the second helium ionization zone, which can be modeled by a damped oscillator model. So here we consider the key parameters, which are the amplitude, A, helium-2, the period G, helium-2, and the phase, phi, helium-2. So with this method, we are able to study how the amplitude, the period, and the phase behaves as the stellar evolution proceeds. Here we will focus on analysis on the amplitude and the phase. So starting with the amplitude, which is represented as a function of delta nu. So here the color code is the following: RGB stars in blue, helium burning stars in red, unidentified evolutionary stages in gray. And for each stellar population, we compute the medians. So here we can see that the typical difference between helium burning stars and RGB stars is that the amplitude is higher during the helium burning phases. So why would we expect such behavior? If we compare it with what we would expect according to stellar models, so where the RGB is represented in blue, the early clamp phase up to the early asymptotic giant branch in orange and the HB in red, we observe similar differences between helium burning phases and shell hydrogen burning phase. So what does it mean in terms of physical structure? If we take back the gamma 1 profile, we would expect the strength of the variation in gamma 1 to be more significant if the amplitude of the... So we would expect the modulation amplitude to be more important if the strength of the variation is more important. if we represent the strength of the variation HLM2 as a function of delta nu, this is what we observe. We are clearly a higher strength of the variation at fixed delta nu between helium burning phases and RGB phase. And we can even go deeper in our analysis because we can relate the strength of the variation in gamma 1 as a function of the temperature in the second helium ionization zone. We see that there is an unequivocal relation between the two quantities, which means that for a given temperature at the second helium ionization zone, you would have a given variations profile at the second helium ionization zone. So the difference that we observe between helium burning stars and RGB stars in terms of mode amplitude can be explained by a different thermodynamic state of the convective envelope related to the temperature at the second helium ionization zone, which is the first important conclusion of this work. Now we can look at the validity of the asymptotic pattern at low delta nu, so at high luminosity stages. Here you see that below 0.5 microhertz, which correspond basically to 40 solar radius, you would see that the amplitude of the modulation, which is expressed in units of delta nu, is of the order of 10% the value perturbed itself. This means that the perturbation introduced by the second helium ionization zone delta nu is equal or higher than 10% of its actual value. Given that in the expansion, theoretical expansion, the glitch signature is considered as a perturbation, here this assumption is no longer valid. So we may wonder if the validity of the asymptotic approach for this high luminosity regions is valid or not. So now, if we move on the analysis of the phase modulation as a function of delta nu with the same color code, here we can see a negative difference between negative phase difference between helium burning stars and RGB stars. Here, this negative difference has also been reported by the works of Matura and his collaborators in 2015, who associated this difference with the difference in the acoustic offset epsilon between RGB and red clump stars. In our case, we still observe this phase difference, the same order of magnitude, which can explain the typical difference that we have between RGB and HGB stars. So the physical basis on which the classification method relies between RGB and HGB stars is based on the signature of the second helium ionization zone, which is the second important conclusion of this work. So what can we conclude from the first part of this work? There are clear structure differences between RGB and HGB stars, which can be probed thanks to the signature of the second helium ionization zone. The first one is related to the different thermodynamic states of the envelope. So the temperature at the second helium ionization during the RGB is more important than that on the HGB, which causes gamma 1 variation that is less important during the RGB compared to the HGB. So the glitch signature is more important during helium burning phases. The second conclusion relies on the stellar classification between RGB and HGB stars. Matura and his collaborators in 2015 highlighted that the stellar evolutionary effects between clump and RGB stars are encoded in the second helium ionization zone signature. We extended their work to even higher evolutionary stages, so between RGB and HGB stars, thanks to a seismic analysis of their oscillation spectrum. This analysis opened the opportunities for other works. For example, we Here, I mainly focus on the analysis of the mode frequencies, but we can also extract the mode height, the mode width, which can be used to investigate physical processes behind mode damping on the AG, which I won't develop here. But in a second, we can also characterize with the seismic parameters the asymptotic general range bump, which can be used to constrain stellar models according with the works of Diego Bossini and his collaborators in 2015, which is what I'm going to develop here. So up to now, we mainly focus on evolved stages of RGB and AGB, which includes a large range in the Armstrong-Russell diagram. Now we focus on a narrow region in this diagram, specifically the AGB bump, which manifests as a turning back in the evolutionary jack. So this turning back is caused by the onset of the helium burning shell, which pushed away the hydrogen burning shell, and so it cools, and the envelope contracts and heats, which explains the drop of luminosity that you can see here. So the envelope continues to contract at a point where the hydrogen burning shell reignites, and so the convective envelope can move outwards and the luminosity increases. And the star resumes its ascent on the asymptotic general range. So the AGB bump has been firstly identified in the column-related diagram of globular clusters, so in the works of Ferro and Poulonnet in 1992, which is illustrated here for the globular cluster N13, studied by Gallardi in 1998, where you can see that the AGB bump manifests as an overdensity of stars after the core helium burning phase in observations. This overdensity can be also highlighted in the Kepler data, thanks to the works of Diego Bossini and his collaborators in 2015, where you can see that for a specific bin of mass and metallicity, we are able to locate this overdensity at a given luminosity. However, this has only been done for a specific bin of mass and metallicity. Here, we cannot know the dependence of the AGB bump position with stellar parameters with Kepler data only. However, as you can see, following the theoretical models of Poulonnet in 1992, there are interesting properties that can be inferred from the luminosity of the AGB bump as a function of the metallicity. Here, at very low metallicity, so below -1 decimal exponent, we expect the luminosity of the AGB bump to be constant. This is very interesting properties because if we can show that the AGB bump, the luminosity of the AGB bump does not depend on the metallicity, they can be used as standard candles, which are objects for which the luminosity does not depend on a given stellar parameters. So this would be the metallicity in this case. And if you look at even higher metallicities, so above -1 decimal exponent, you would see that according to the theoretical models of Azres and Sargentini in 1999, you would see that the luminosity clearly depends on the metallicity. Not only on the metallicity, but also on the stellar mass. Here, you see that as the mass increases, the luminosity increases. So in this part, we would like to investigate the metallicity and mass dependencies of the AGB bump. And secondly, we would like to assess the potential of the AGB bump to constrain stellar models. Okay. So how do we locate the AGB bump in observations? So basically, we took the same sample of stars that we used in the first part, but to have more bins of mass and metallicities in which we can locate the HGB bump, we add the test targets. So here in the Kepler targets, I highlight the position of the HGB bump, which manifests as an overdensity here, and the clump stars, which are predominant above 3 microns in the delta U. Here, we reject them in our sample of stars as they are way off the overdensity caused by the HGB bump. And in our study, we include both RGB and HGB stars in our sample of stars, because we want to keep as many HGB stars as possible. We don't want to reject potential HGB stars that have been identified as RGB stars by the classification method. So here we have, for example, a sample of star in a given bin of mass and metallicity, so at a low mass, where we represent in a seismic diagram the 2D histogram of our sample of stars. So similarly as before, nu max instead of the luminosity, but there is an inverse relation between the two quantities. Here we reproduce the HGB bump with the same method that has been used to locate the luminosity bump on the red giant branch, performed by Sania Khan and her collaborators in 2018. So here we use a statistical framework to fit the data set with multiple models. So what does it mean? Here there are mainly two kinds of population of interest. The one that belongs to the overdensity due to the HGB bump, which is represented with the blue diamonds and 1 sigma and 2 sigma ellipses in dark blue and light blue, and the other stars that do not belong to the overdensity caused by the HGB bump. So this would correspond to the RGB and HGB background, which can be modeled by a normal distribution around a linear term in a nu max. So here we have the linear term in a dark red, and around the light red dashed lines, which corresponds to the normal distribution around this term. In this way, we are able to extract the location of the HGB bump in several bins of mass and metallicity. So here, this is, for example, the location in nu max as a function of the metallicity, where the mass is emphasized in a color bar. So first, look at the variation, focus on the variation with the color bar. Here we see that the higher the mass, the lower the nu max at the HGB bump. We can see that the typical variations that we have with respect to the mass are more important than the typical uncertainty that we have. So this is a strong evidence of a mass dependence. This indeed agrees with what we would expect from theoretical works. As you can see, as the mass increases, the luminosity increases. So equivalently, delta nu decreases, and which is what we observe. Now, if we look at the location of the HGB bump, not in terms of nu max, but in terms of effective temperature, so the similar graph, we see that the higher the mass, the lower the effective temperature. However, here, the variations that we have with respect to the mass are of the same order of magnitude that the typical uncertainty with which we extract the HGB bump location. So this conclusion needs to be confirmed. And if we gather those two conclusions all together, so the higher the mass, the lower the nu max, and the lower the effective temperature, this means that the spacing between the clump and the HGB bump increases as the stellar mass increases. So what does it mean? If we locate the HGB bump in the evolutionary track with the dotted cycle here, at higher mass, the distance between the HGB bump and the clump face increases along the stellar evolution, which is the first conclusion. Now, if we focus on the metallicity dependence, so here we look at the variation of the HEBM position in Umax along the metallicity axis. We detect slight metallicity effects in Umax, which are mostly visible at high mass. Here you see that the higher the metallicity, the higher the Umax. This is what we expect from theoretical models. As you can see from the work of Alves and Sargentini in 1999, there are clearly metallicity effects which are expected at metallicities that are higher than -1 decimal exponents, which corresponds to the range of metallicities that we use in our sample of stars. But at even lower metallicity, you can see that the metallicity effects fade. The metallicity effects are less important. So what can we conclude from this metallicity dependence? At least at high metallicities, the HEBM position in Umax equivalently in luminosity varies with the metallicity, so the HEBM may not be used as standard candles, at least for a metallicity that is higher than -1 decimal exponent. At lower metallicity, we need further investigation with a larger sample of stars at low metallicity. This way, we have extracted the position of the HEBM for several bins of mass and metallicity, so we can try reproducing this HEBM location thanks to stellar models, which is basically what we are doing here. So here you can see the location of the HEBM in observations with the blue dots here, with the 1 sigma and 2 sigma ellipses. We build a reference model with a given set of physical parameters. And we can see that with this reference model, we cannot reproduce the HEBM location. So here, all the other data points that you can see on this graph corresponds to the same reference model, but for which we changed the physical parameter of the stellar models, or when we added physical processes. So here it seems that the model that best reproduce the observations as that when we include helium core overshooting. So when we add an additional mixing layers above the convective core of core helium burning stars, which has been highlighted in the works of Diego Bossini and his collaborators in 2015 for low mass stars. Now, if we look at high mass stars, you would see that including helium core overshooting is not sufficient to reproduce observations. Here you can see that the models is clearly off the observations, the 1 sigma and 2 sigma areas. In this case, we need additional physical parameters to reproduce the HEBM location. For example, by including additional mixing, such as rotational mixing, which allow us to reach the position of the HEBM in terms of Umax. So, what can we conclude from the second part? For the HEBM position, when the mass increases, the Umax and the effective temperature decreases, which makes the higher luminosity gap in the evolutionary track between clump stars, the clump phase, and the HEB phase. This is the first conclusion that we have from observations by combining Kepler and thèse observations, and we also highlighted metallicity effects in Umax, at least for high mass stars, and for metallicities that are higher than -1 decimal exponent. So for these stars, the HEBM stars may not be a suitable standard building. And for lower metallicities, we need further investigations. This was from the observational window. Now, from stellar models, we have shown that we are able to reproduce the HEBM position with including physical processes such as helium core overshooting or rotational mixing. Most important conclusion is that the calibration depends on the stellar mass. So we are able to calibrate mixing processes with the HB bump position. So now the final remarks and prospects of this work, which are numerous. So first, in my PhD, I developed an automated code to derive seismic parameters of thousands of RGB and HB stars, which allow us to extract, for example, the mode frequencies, the mode heights, the mode widths, which can be used to constrain the stellar interiors. With the help of stellar codes, such as MESA and ADPLs, we were able to model the evolution from the early stages of stellar evolution, so the main sequence, up to the HB, high luminosity stage of the HB. And for each of these stellar models, we could extract the theoretical adiabatic pressure mode frequencies, which allow us to investigate the structural difference between HB and RGB stars. Finally, I developed an automated code to extract the HB bump position in the Kepler and thèse data, which allowed us to study the metallicity and mass dependencies of the HB bump position. So this gives rise to many interesting astrophysical results, including the identification of the physical basis to identify RGB and HB stars, which is based on the secondary ionization zone signature in mode frequencies. We also highlighted on the basis of seismic signature. So we highlighted seismic signature of internal structural differences between RGB and HB stars, and we highlighted that the HB bump at higher metallicities than -1 decimal exponent, that these stars, the HB bump may not be used as a standard condom. And finally, the HB bump position can be used to calibrate mixing processes in stellar interiors. So this work gives the opportunity, so opens many opportunities, not only in stellar physics, but also in other fields of astrophysics. So starting in stellar physics, we could expand the seismic analysis that we have done on RGB and HB to other stellar evolutionary phases. For example, during the helium flash stage, for which we lack observational evidence. So to this end, we would characterize the mixed mode pattern, which is sensitive to the innermost layers of the stars. In the same time, we could also extract the buoyancy glitch signature, as presented by the works of Margarida in 2015, which arises from the transition between the convective, so buoyancy glitch, which is caused by the transition between the convective core and the radiated part of the core. Second, we can investigate the rotational profile of clump stars, thanks to the MESA model we have computed in this work. Particularly, the recent works of Benoit have shown clear evidence that the rotational profile in the core of clump stars varies as the stellar radius to the power -2. And with stellar models, we can investigate if this relation can be explained by a solid body rotation or an homologous rotation. In other fields of astrophysics, for example, in astrometry, we can assess the potential of the HB bump at low metallicity to be standard kernels. So here we would need a larger sample of stars, which can be provided thanks to the data collected by GU and his collaborators this year, which provide a sample of 5 million of stars, including stars on the RGB and HB at low metallicity. Finally, we can also study the impact of helium core overshooting not only on the HB bump, but also on more evolved stages, such as on the core of white dwarfs. Indeed, the mode periods are sensitive to the innermost layer of the star, including the core chemical stratification. So we can probe the deep core chemical stratification with their signature in the period spectrum, according to the recent works of Gia Michele and Charpinet, of Stéphane Charpinet recently. And this will conclude my presentation. So I thank you all for your attention.
Thank you for your presentation. You're on some time. It's good. We can start now with the questions. Valérie,
Yes.
please.
Okay. Thanks for this presentation. It's a very dense work. You did a lot of things, both modeling and observationally. And you never forget to make the link between the two, even in very theoretical figure. You put the limits on what we can observe and so on. So I really appreciated that. And also, you always kept in mind the hypothesis and the assumptions that are behind the formula that we are using in the asymptotic formula and so on. So that's another very good quality of your work. It's a very small remark, but I find the title of your PhD thesis is a little bit unfair toward your work, because you didn't only care about the HB star, but also about the red clump and the RGB tip stars and so on. So you compare a lot of things. So yeah, I would have named it high luminosity giant instead of only HB. You know, it's just a detail. I'd like you cite several times around the manuscript the mirror effect, the fact that the core is contracting and the envelope is expanded. Could you explain a little bit with your hand, with the physical, what are the physical reasons why at several stages the core is contracting and the envelope is expanding?
So, so as far as I can understand, this is due to the conservation of the kinetic energy in the envelope, and the total energy in the envelope and that in the core, which will induce that a potential contraction or expansion of the core is related to the dynamics of the core according to this conservation equation, and yeah, what we call the mirror effects are that while the core contracts or expands, the envelope will do the reverse evolution. And this can be explained by the conservation equation of the total energy in the core and on one hand, and in the envelope on the other hand.
Yes, because in the manuscript, it's page 24, I don't know if you have it in mind, you say that it's because since most of the solar mass is concentrated in the core, we can consider that the mass of the core is much higher than the mass of the envelope. And I was a little bit surprised, because it's, yeah, even in the subgiant phase, is it really true? Because, yeah, the core to me is going along the subgiant and the hydrogen shell burning, so to reach the 0.47 solar mass and so on, while the envelope must be much higher. I was surprised to see that.
In terms of mass, I don't think that the mass of the core is increasing. I think it's, as far as I remember, it keeps being at the same mass, but then when the RGB evolves, the star evolves on the RGB, then the mass of the core decreases. As far as I remember from exponent diagrams.
Okay. Yes, to me, the mass of the core is growing by hydrogen shell burning, so the mass of the helium core, I mean. And then it reached something close to 0.43 solar mass, and it triggered the helium flash. But yes, okay.
But this one was one of the assumptions to reach the relation that
I think yes, from what you explained, equation 2.4 and so on. Yeah. That's why I wanted to ask you more physically, you know,
but
because I was a little bit
physically
puzzled.
is the conservation of energy.
Okay.
The duration that I have written is
Better.
derived from these conservation equations.
Yeah, maybe, I don't know. I have 10 minutes or what? I liked your tool to extract automatically the frequencies with the autocorrelation. Is it something that you developed from scratch, or was it, you know, can you tell me a little bit the history of this tool, let's say, because, yeah, I find it interesting, yeah. It's the first time that I understand well how we can extract the pulsation frequency for RGB, RGB stars, and so on, because, you know, I'm used to a classical pulsator, let's say, and
So I'm just getting back to.
yes. And as a consequence, such tool wasn't available to do that before your work.
Okay, so basically what I have developed is to build this template spectrum. So here, the height of the peaks that you can see reproduces simply the shape of the bump in the power spectral density that we would expect from a dumped for modes that are dumped with the Lorentzian shapes here. And yeah, what this procedure tells us is that we can extract by varying delta nu the optimal delta nu that we would expect by overlapping the template models and observations, and we can extract the identification of the modes. So that's, say, the radial order and the degree hand. And by looking around the maximum correlation of the template oscillation spectrum, we can extract the frequencies of the modes. But here, of course, we do not extract, like it is presented right now, the height and the width. So there is another step in the process. I think it's this one. So here, because of the nature of the excitation and the stochastic nature of the modes, we expect them to manifest as a Lorentzian profile in the oscillation spectrum. So a radial order per radial order. So here we would have 3 modes at most. We fit the modes with a Lorentzian profile. So which we can extract the frequency, the height, and the width. And yeah, that's basically how I extract mode characteristics.
Could you use this tool to extract the mode properties of solar-like pulsations on the lens sequence?
The limiting factor here is the shape of the template spectrum that we are using. In this case, it mostly works with very intense pressure modes. If we add mixed modes, for example, on the Radian branch, it may confuse the code may confuse this pair of dipole of quadruple and radial modes as
on the main sequence you don't have mixed modes.
But yeah, but for main sequence stars, I think that it could work in this case. We just need to adjust the template, right?
Okay. Another technical question about yes, this pressure-dominated mode and so on. So yes, with editors, you suppress the computation of the mixed mode, and you computed the equivalent of pure P modes that are the closest and so on. Could you explain a little bit why you had to do that? Is it because of numerical difficulties?
Yes.
Or? Yeah,
exactly. In fact, the mixed modes in red giants, we require like thousands and thousands of mesh points to properly resolve the eigenfunction of the modes. So to avoid this this time-consuming step for hundreds of models on the RGB and on the HGB, we prefer suppressing the G modes in the core by considering by modifying by hand the Born-Weisseler profile in this star as an input on the 80 poles code. Of course, we do not modify the MESA models, just to compute the mode frequencies.
Another question, it concerns figure 8.1, 8.5, 8.6, and so on. I think you have shown some in your presentation. It's on chapter 8. I think it's on slide a little bit earlier than slide 20, because I've seen. Oh, it's about the errors. In fact, you quote errors, and in the text, let me take the figure here.
By any chance,
on this figure, you know, and you have shown some.
Some of them, yeah.
And how did you obtain such numerical error? You say some are for delta mu below 1, and some are for higher. I didn't understand exactly how you did obtain. I didn't understand it was observational error, numerical error, or error provided by a addition. So
it was a numerical error, actually. So it is the error that I'm showing on this graph, for example.
Yes, exactly.
So the typical error bars that are shown here are obtained from are representative of the precision to which we extract the mode parameters with the method we use to extract the mode parameters, so with the fitting process.
Okay. Yeah. Okay. Thank you. I had also two more physical questions related to the mixing processes on the RGB and HB phase. So yes, in a MESA, so you don't have the semi-convection. You know, that's very well modeled, let's say. And for example, I from what I did with our stellar evolution code, for example, is that the semi-convective zone compared to the overshooted zone is much higher, in fact. So I was wondering, for example, for the higher mass star, that you have an overshooting of 0.5, and you are still far, and you say it's unrealistic, and you want to add the rotation and so on. But what do you think, to which extent the fact that you are missing the semi-convection explains such kind of result, that even with a very high overshooting, you are still far? But yeah, I had a little bit difficulties to interpret this number of overshooting needed when you know that you don't have the semi-convection.
So I think this is normal that you had some difficulty to interpret this, because actually, as you could see, I used many physical ingredients to try reproducing the HB bump position. And in this case, we use many physical parameters as a first exploratory work to see how the semi-convection well, actually it was more about overshooting, but we ended up having issues with overshooting as it impacted the shape of the edge bump without considering semi-convection. So, so basically, why we choose to implement semi-convection is that in the MESA code, it is complicated to disentangle the limit fixed by the Bar-Schwarzschild criterion. So as a function of the radiative gradient and the adiabatic gradient, and the overshooting region. For example, here in this clump star, the convective boundary will be fixed at the position where the adiabatic gradient is equal to radiative gradient. And in this profile, the ratio between the two does not go above 1 again. And at a specific step, we see that the ratio between the two quantities goes to 1, then it increases again and drop below 1. So in this case, MESA struggled to set the boundary of the convective core because the overshooting is by definition an additional layers of where mixing occurs, and it struggled to identify if this is at this point or at this point where the convective core boundary of the convective core can be set. So in this case, we use an additional treatment that has been developed by Diego Bossini in 2017, which allows us to set the limits of this convective boundary at the first local minimum of the ratio between the radiative gradient and the adiabatic gradient, and not at the local maximum. Yeah. So this is how we adopted the overshooting criterion in conjunction with the semi-convection. Now I have I did not have time to look in details how other codes were managing this semi-convection region, at least for 3D models. But for 1D models, I don't think there are like many ways of proceeding, like using a homemade method to deal with the semi-convection.
A way that is done is to impose that the gradient of temperature is equal to the adiabatic gradient for the flat region.
Then for the extent of the semi-convection, actually I didn't do that into details.
There is no module in MESA that model at all the semi-convection?
We can choose the efficiency of the semi-convection, similarly with an alpha factor in fraction of the pressure scale height, but actually, I think the layers was not that. I did not choose a very high semi-convection in those models. I used the typical values.
Yeah, but yeah. So the little correction that you adopted. So you can say that the overshooting you have to adopt includes kind of the semi-convective region. So it's not that disturbing that you have to that you found so high overshooting. I don't know.
Actually, I didn't choose a very high semi-convection factor efficiency. This was not very the kind of physical processes that we explored yet. We only choose typical value for the semi-convection so that the HBM position that we extract is not affected by the additional artificial convective layers that could result from not taking into account semi-convection. we did not really explore the effects of semi-convection, how the HEV is impacted by choosing such or such semi-convection factor.
Fundamental phenomena that occur in beryllium burning models. So, yeah, if you want to constrain the mixing processes above beryllium burning, it's something that must be taken into account. But it's still interesting because, yeah, in hot subdwarf and also in white dwarf, we found from seismology that we need very big code to reproduce the G mode observed, both in hot subdwarf and in white dwarf. So
with semi-convection?
No, it's for master of seismology. The seismic parameter indicating that the helium burning, the helium burning core is quite big, much bigger than what you obtain. It's a static model, so it's really the seismic model. It's not obtained with stellar evolution. But if you want to reproduce that with stellar evolution, you need to put some convection and then maybe high or very high overshooting if you want that convection and so on. So the fact that you have to put an overshooting parameter equal to 0.5 plus, in addition to the rotation, for example, to reproduce the HEV location. Yeah, it's still not of mixing processes at that's what I need.
But this is the issue that we face at high mass actually, because this was the last slide before the conclusion.
Yeah, you said it in your conclusion. You cited white dwarf.
Yes, to reproduce the position of the HEV bump at high mass, we need unrealistic mixing parameters.
Yeah, that's what I said. Is it really so unrealistic?
Actually,
it's a complicated problem.
Yeah, this will be the next step of this work, actually. Because this was only a preliminary work to see what physical processes.
Yes, you demonstrate that the location of the HEV bump has the potential to constrain the mixing processes on the helium burning phase. But yeah, more sophisticated models for the semi-convection and so on will be needed to go in.
Yeah, of course. Here, I'm not giving clear parameters that should be used for a given mass and metallicity. This is just a preliminary work for which we study the impact of physical processes. We are not telling you should take these values of the parameters to reproduce such interval of mass, or etc. It remains exploratory.
Okay, thank you, Guillaume.
Okay, yeah, I finished.
Okay, so there is still a little discussion.
Yeah.
Okay, thank you. Now, Stéphane, go ahead.
Thank you, Guillaume, for your presentation, which I found very, very well done, actually, and which applies very well the manuscript. So what I liked, really like Valérie, about your work is first it's a very substantial work which extends methods and ways to extract seismic information on phases of stellar evolution that were not really explored before. And especially HEV, which for me is a very interesting phase because it's the place where many things are happening which are very uncertain for many of them, and which will affect what white dwarf will be at the end, especially what happens in the core. So the fact that you both developed the observational aspect, like the extraction of the seismic information, and in parallel the modeling of these seismic signatures, so that you can relate very clearly what we observe and connect that to some physical difference between the RGB and HEV is, of course, very interesting aspect of your work. So the modeling part was a bit dense sometimes. Maybe you could have summarized a bit more to get the essence of it more, like you did in your presentation, in fact. But overall, it's going to be probably a good reference for future work that will be done on this subject. So if I move to the questions, so we were talking about the helium burning core, so maybe I should stay a little bit on this, just to continue the discussion a little bit more. One thing I found, of course, I understand what you did is really exploratory. So you essentially adopted the prescription and with some parameters, which is a overshoot parameter in that case, and you explore what this parameter does. But as we discussed, this phase of the core helium burning phase is actually not just a matter of parameters, it's also a matter of prescription, how we describe the phenomenon that is occurring in that phase. So the work you have done this clearly has to be extended to explore many other things. And one aspect we didn't mention in the discussion here is, for instance, at the very end of the core helium burning phase, there is an instability that occurs, which we call the breaking pulse, which people tend to remove from the models artificially, saying it's artificial. But it's not really clear, in fact, whether these things are happening or not. And I suspect that if the breaking pulse occurs, that will affect also your results and the position of the AGV. So in your calculation, so you adopted the code MESA. I guess it was for simplicity. Or why didn't you use Sesame, for instance?
The problem is very simple. It's because with system we cannot go beyond the helium flash stage.
That's a very good business.
So otherwise, rest assured that Yulin would have told me to use the system. I assume at least.
And in your calculation, you use the multiples also, and you mentioned in manuscript a little bit that there were some difficulties in calculating the modes in those evolutionary stage, and even at the very for the high luminosity ones, even when removing the mixed modes, with the trick that you are using, you got some difficulties also to make it converge. I was wondering, there is also JAG, which is provided with MESA. Is it something you have explored? Is that a code that maybe more robust?
I haven't explored it with Jaya, but there is a way to explore it, because this is basically in the MESA code. There are two options for computing the oscillations, the oscillation modes. We have adipoles and Jaya. In this case, I mainly focus on adipoles, but with Jaya, I think that would be an interesting way to check if the frequencies that we are computing are consistent with what we could obtain with other oscillation codes. But I think, yeah, basically the trick we are using could also be implemented in the Jaya code as inputs for the stellar models, and I think this could be done also.
Okay, and if you get interested to the very high luminosity AGV, so you mentioned that at some point you're going to very evolved stars. So your assumptions are somehow break down because you no longer see modes which are really in a certain regime, right? So do you think that it would be possible to exploit those objects by doing direct calculation with like Jaya and to do some, so it would be a very different approach, but then maybe get some information that I do the direct modeling of the stars instead of asymptotic fitting.
So you mean in observational side or modeling side?
Well, in the observational side, you're using the asymptotic condition to extract. So this breaks down, I guess, you cannot easily, but you could develop another way to identify maybe the modes. But then also, if you want to model that, so having some, you could no longer use, I guess, the seismic quantities that we use in the asymptotic regime, because they would be meaningless for the stars. So you would have to try to do direct modeling. Something that is really difficult to achieve.
This is a bit out of range of what I am doing, because I think this is a kind of a project in itself.
Sure.
And I think even with a theoretical expansion, we struggle to give an analytic expression for the mode frequencies at very low radial orders.
What I'm saying that is because there is actually a lot of information which is encoded in low radial order things, although they are less easy to interpret because they are outside the asymptotic relations. So that might be interesting to explore project. So if we go back to the method to extract the properties of the seismic properties of the stars. So you applied it to a lot of stars or objects, so it's automated. But I was wondering how automated it is, at which level it is automated. I mean, you just press a button and you automate it, or you still have to put your hands in it. In particular, because from my experience, like curves on thèse, for instance, or Kepler, there are always some artifacts, things from one star to the other, which are so you often have to correct like yourself. And I was wondering if you need some preconditioning things to do to the like before you can apply it.
So yeah, of course there are prerequisites. The method I'm using are directly used on the oscillation spectrum, on the power spectral density. I am not doing the light curve fit.
So those are already preconditioned.
Yeah.
With the tools. Okay.
Yeah. To apply the automated code, I need the power spectrum. And also, because with the method I am using, so to overlap the template and observe oscillation spectrum, I also need kind of a rough estimate for the value of delta nu, for example, just to not start at currently off the frequency range of oscillations.
That's actually another question I have, is whether when you do this cross correlation, these correlation things, if you have several solutions possible, so actually by choosing a initial guess of values, you somehow restrict a lot the scanning thing, just to avoid maybe having several solutions. Is it always clear?
Yes,
or
it is
sometimes ambiguous.
In fact, it is clear because of the shape of the template spectrum that we are using. As you can see, we adopt different heights for the Lorentzians, following along the power excess of the oscillations. So
you have included the expected new max, right?
That's it. Yeah. So this allows us to not mix, for example, well, it can happen if the modes are not as visible as they should be, but in most of our stars, we do not mix, for example, the order n and n plus 1 because of the height that we adopt on the template spectrum. Of course, it can happen if the modes are not clearly visible on the oscillation spectrum, but these are not these stars are not predominant.
Okay, and when you go to high luminosity objects, so you tend to see less modes, right?
That's it.
Then the methods.
Of course, but this is actually not the main difficulty here. This is basically the first difficulty that we encounter. Unfortunately, I don't have any example here, but at low delta nu, the pattern at the fixed radial order is not very clear at low delta nu. It means that with this template, this is not straightforward that, for example, this mode is a radial mode or a dipole mode or etc. We need to expand the analysis to very low delta nu. We need to consider several templates for the oscillation spectrum. We cannot only blindly follow the adjustment at low delta nu with only one template spectrum, because of the validity of the asymptotic expansion may not be valid. Like, the asymptotic expansion may not be valid. We need to consider other pattern until theoretical expansions will be made, but it's difficult.
And in that process, because here your template is assuming that instance, right?
No, actually not.
But maybe it's okay for this kind of stuff.
Yeah.
But if it's not okay, could this actually influence your estimates?
No.
Just imagine one of the modes you fit is actually a blend of triplets.
I would say no,
because
because
resolved, but that enlarged.
With this example, I would say no, because here we only observe pure pressure modes. So here we don't have the azimuthal order does not comes into play in this case. So the rotational splitting, we do not observe observational splitting for these stars.
Okay, they are not resolved, but they could be here still equal to what?
Yes, that's true. They may be blended with within the Lorentzian profile here, actually.
That could have an impact for, you didn't really talk about that in your presentation, but for the measurements of the
For the width, yeah, of course. And this is, but beyond the rotational splitting, there is also the limitation where I think, no, I say a few words about it. Yes, I have the example. Yeah, there. So here, I think this is the most. This is the most. The limit. This is the one of the stars for which we clearly observed the mixed modes pattern at very low delta nu. So this is noted for 2.7 microhertz approximately. And as you can see here, we are limited by the frequency resolution. For we cannot properly resolve those mixed modes. And if we go at even lower delta nu, in fact, because of the frequency resolution, but also because the spacing between these dipole modes shrinks, it will rather reproduce several mixed modes, but as seen as one single mode. So this is not only a matter of rotational splitting, but also because the spacing of within the mixed mode pattern becomes smaller and smaller relatively to the frequency resolution.
Okay, maybe one question about the glitch. One is slide 16. Yes, so in that fit, actually we look at the L equals 0 modes, for instance, they are not really fitting very well to the curve. So I was wondering if you have an explanation for this first, and second, whether whether actually since AGV starts, there are also other parts of the stars which may show some rapid change of the so there is transition between different positions. I was wondering whether the glitch could be affected too by other the main glitch of the due to the helium could be also distorted or affected by other glitches that can occur in different parts of the stars. And I was wondering whether, since the L equals 0 modes, they tend to go deeper than the L equals 1 and 2 modes, not bounded, that it is not bounded anymore. Whether they might be affected more. Have you explored this a little bit, or just? I mean, is it really representative of what you get for this example, or do you have some example where all fits together?
So here you have the perfect example that by only using radial modes, we are not able to reproduce with certainty the profile, the signature of the secondary ionizations of the field. If you only try to fit the modulation with radial modes here, you would not be able to extract the signature because you wouldn't have enough points, data points, to make sure that you can extract the signature with reliable results. So here we made the assumption that the modes that we see on the oscillation spectrum are of the same nature, so pressure modes. Because, for example, for the dipole modes, as you could see in the previous oscillation spectrum, we can mainly observe one mode, which is the modes of lowest inertia and which is the closest to the expected pressure modes. The works of Anne-Marie Bronco, for example, have shown that at a delta nu value that is below 3 or 4 microhertz, then that the modes of lowest inertia for dipole and quadrupole modes can be used without deteriorating the fitting process. So we follow this assumption so that we use both dipole and quadrupole modes in the fitting process. Because here they are required if we want to do this process, because otherwise, according to the Nyquist criterion, we would not make sure that the period is reliable or not. Because if the period is quickly varying with only 3 points, we would not make sure that this result is reliable or not. So we are using both radial and non-radial modes. This work. I think this answers the first part of the question. The second, I don't remember.
The second, it was L equals 0.
So if the modes are of the same nature, let's say pressure modes, we would expect these modes to be affected the same way, approximately.
Because the L equals 0, we know for sure.
Yes.
It's not the case for the other one.
But this is the main difficulty for this involved star, is that we do not have a lot of modes that can be observed. Here, this is an extreme example, just below 1 microhertz in delta nu, where we have around 4 modes, 5 in the best case scenario. At higher delta nu 2 micros, we have more modes, but well, around the limit delta nu 2 micros, only using radial modes is not sufficient to reproduce observation. And I think I have an illustration for that, because in my presentation I mainly focus on the amplitude but not on the period. I think this one is fine. Yeah. So in if we want to use the only the radial modes, the lowest limit we can have when only using radial modes to make sure the results are reliable are that are above, with a period above 2 units of delta nu. So here it would correspond to something higher than 3 microns. But below 3 microns, from what we expect, we cannot use only the radial modes blindly, assuming that we extract a reliable signature. We need those non-radial modes at very low delta nu. And by taking the non-radial modes into account, because the spacing between consecutive radial and dipole modes is reduced by 2 compared to 2 consecutive radial modes, then we push the limits at the parameter G equal to 1. So all the periods that we extract above the period G equal to 1 are susceptible to be representative of G. At least we can reliably extract the periods for this stars.
And how would you assess the bleach fitting method as, in terms of reliability to separate AGB and RGB? Because you mentioned the other 2 methods, which one is based on the scope set, which actually is related to bleach. And the other is on the fitting envelope of
yes.
the method from the one. So you said, you mentioned in your manuscript that at some point both methods become very reliable at low delta nu. Could you do you think you could improve or push even further actually the method of classification to lower delta nu with the bleaches?
What I studied in this work is not proposing a new classification method. Actually, the method that Thomas Kellinger used in this work is maybe mostly efficient compared to the glitch modulation I am fitting. This work was for just to bring the physical basis of this, not proposing something new.
But you developed a quite sophisticated method to extract also.
Yeah, of course. Yeah, of course.
That could
actually
be used to improve the classification.
I can use the measurements of epsilon I am using, affected by the glitch, to do similar classification as Thomas Kellinger did.
One question?
Okay, just.
Okay, thank you. So Margarita?
Yes. Thank you. Okay, just I will not repeat. I completely agree with what both previous people said with respect to this. I think you touched on many things, theory and also data analysis and so on. Like it's very comprehensive. The nice thing about it is that it opens a lot of windows also in terms of research. So I would like to discuss a little bit a few things that you left out, but it's in your thesis paper. But before I do that, just to complement on some questions that have been discussed already. I wonder if you can show again the figure of the glitch where you show for that star, just 2 slides previously that we were discussing with Stefan, one on the star where you should be doing. Because I was looking at it and I was from a question to me. No, it was actually yes. So one of the things that I missed, I guess, in your thesis and in the paper as well, is more examples of individual stars. I understand you're doing ensemble studies, and that's the purpose, but it helps us believe the results to see curves like that, fits like that. I don't think they were in the paper,
no.
But this is, I think, this is the only one that is there. And one thing that, for instance, I wanted to ask you, just looking out the figure, so it seems that the other guys on all understand. Is that always the case that you do output 0, output 1, output 2, you get uncertainty, similar uncertainty? Because this is from data, right? So is that the case?
So here, yeah, actually on this figure, I am showing the uncertainties that are limited by the frequency resolution.
Okay.
But we also have to, here I'm not showing, but we can also, we should account the correlation between when computing the large separation, the uncertainty at order n+1 and that of order n. So there are correlation.
Yeah,
I am accounting, taking them into account.
Yeah, when you do the fix, you take that into account. Okay. Now I agree with Stefan that it looks like the L+1 and L+0 nodes are not well fitted apart from one of them there. So it's like if the fit was dominated by the in this case. But my question to you is, did you look at many of these fits? Were you happy with the fits that you see in general? You found that they seem to be good for your solutions, seem to be good fits for different type of stars?
I think the most difficult behavior to reproduce is the damped behavior. For example, I used also other fitting expressions. For example, I used so here this is basically the same expression, but with other expression for the amplitude.
Yeah, that's the other question I was going to ask you. I mean, Mathieu used the constant amplitude as far as I remember, right? And so I was going to ask you whether is that by considering the damping, which at least for main sequence stars, so we can static analysis, we expect it to be there. So I expect for pure acoustic mode 0 to be the same as well. Do you think it improved the fits by considering that compared to what Mathieu was, given the number of modes that you have, which is limited, right? Of course, if you have many modes for models, you need damping for sure. But do you think it improved? Did you quantify that improvement? Did you compare with Mathieu's results for subsequent stars?
But basically, so initially I used these many expressions. So one, of course, which is not applicable is this one that we use for the least evolved regions because there are too many free parameters and too few data points. And so I used the constant amplitude. So the amplitude that varies as the inverse of the frequency and square of the inverse. Typically that were studied by Mario Dréau, or in the case of overshooting or not overshooting. And how I made this choice was based on the dispersion of the glitch parameters. I saw that when using a damped, forcing a damped oscillator model, the dispersion of the parameters were.
Yeah, that's a good way to decide that. Because I don't see, at least in the paper, I didn't see that. In the thesis.
Yeah, that's true.
In the thesis, I saw that you mentioned that Mathieu had used fixed amplitude, but non-frequency dependent. I mean, but the reason was not explained. Just one other point that has been discussed, just to add, this is maybe a comment. You make a very good distinction in the thesis, and I think you did it in your presentation, which was Great, actually, I really enjoyed the presentation. You mentioned two problems when you go to very small remarks. You mentioned the issue of the validity of the syntactics, and you also mentioned the issue of the perturbation eventually not being too small. I think these are two different, and you're saying these are two different things. The fact that you are no longer in a perturbative regime can be fixed so far as the asymptotics is still valid. That's what we do for the glitches in the core, for instance. Rather than using a variational approach, you can just assume the asymptotics on each side of the glitch, and you match them through the glitch. That's not a problem, even if it's a large perturbation. The real problem is the asymptotics, because you have to assume some form of the eigenfunction on each side of the glitch in order to get the eigenvalue condition. And if the asymptotics are not good enough representations of the eigenfunctions, then you have a problem. But you can check that by comparing models, check with models. What is the limit in your maths where your eigenfunctions become significantly different from the asymptotic ones, because that's what when they become significantly different, then you can't apply it. But until there, you can probably apply it not through the variational principle, but applying by matching the different models. This was just a comment because that was discussed. Now, what I wanted to discuss with you a little bit more that you don't mention so much here. If you can perhaps show the slide where you had your method and you had the pattern for the asymptotic, the universal pattern there. So that first I make sure I understood what you did.
So this one there.
Yeah, I can be that one. So if I understood correctly what you did, the values for the reduced separations, they are obtained from the template, right? From the best template, is that it? Because you mentioned that the large separation is obtained from the best template. Is it the same for the other parameters? No,
not actually. So here, the template that I use is mainly aimed for identifying the modes, the degree, the radial order. Then the frequencies are extracted directly by looking at the frequency of the peaks around that we have from the template. And with these frequencies, which are not extracted from the template, just around, looking at the maximum of the power spectral density, we compute the seismic parameters.
Okay, so you can do it locally, radial order by radial order. Because that wasn't clear. I thought that this would you determine directly global quantities from fitting the whole spectrum. That this UL would come from just like the large frequency separation. That would come from that global fit, not from completely from individual frequencies. Right.
Yeah, so I assure you that they come from the local.
From the local, okay, yeah. So, and then you do an average, and then you do the average. Okay, that's fine. So then I have a question. So you show in the plots in the paper the D01, the D02, the D03, right? Because you do find the L = 3 modes. I want you to understand a little bit better how often you find these L = 3. I find these L = 3 modes can add information that usually you don't have available. For instance, when we study the photometry, so how often and how trustful would you say these L = 3 are? Is it something that you trust, and is it a large number of times?
So these L = 3 modes are mainly detectable at a delta nu value that is above 2 microhertz. So their signals to noise ratio are large enough to make sure that they are detectable. The problem is that so I stopped the analysis of L = 3 modes. I restricted the analysis of these modes to this operation. I did not fit the L = 3 modes simply because they are not intense enough from the background contributions to be fitted properly.
I understand, but you can then eventually identify that. Once
But
you have you look at then the power spectrum, you can identify them in some cases, I guess.
Around here this is not represented, but when we cross matching the templates and the observed oscillation spectrum, here we are not using A equal 3 modes. This is just in the step after when we.
I understand. Right. Okay. So you're saying that you find them for not for this. Okay. Let me put it in a different way. The regime where you find them, it's probably a regime where the P modes are not purely acoustic anymore, right? We cannot assume them to be purely acoustic anymore. The alphas one to me. Because what I wanted was to combine the 1 and the 3, you see. But I wanted them to be purely acoustic, and so I needed a regime in each. Because okay, let's just to finish. Let me. You say several times in the thesis that the reduced small separations, which I guess from your definition are essentially the ratios. Although I'm not sure how you calculate without the new in the denominator, but I guess it's as in the ratios. And that they provide you information about the interior of the star, right? That would be a great way also to distinguish between the AGB and the RGB, right? From what you've shown us, right?
This is actually what Thomas Klinger is doing. He's not doing it. He's only doing it with the epsilon.
The epsilon, yeah. But I'm more interested in the reduced small separations, and so and I'm interested for a particular reason. Do you understand? So when you say the small separations, forget about the reduced, just the small separations L02, that they give information about the core. Without thinking about the asymptotic expression, right? Do you understand why they give information about and you explain in simple terms, in terms of what the waves are doing? Why is it that they give information about the core?
Yeah, because for example, for the second-order ionization zone, so the D0L are sensitive to gradients of sound speed as the integral over the whole star. And for example, this the gamma 1 profile, which show clear variations in the gamma 1 profile, which is in fact related to the sound speed. We can detect. We could detect this signature of the second-order ionization zone in the small separation parameters.
In the case of the stars that you study, from what I saw in your plots, I think that the lowest frequency ones, I think the helium glitch is located in the inner part of the acoustic cavity, right?
Yeah,
so it's
not the core.
So not the core, but it's in the inner part of the acoustic cavity, not in the outer part. So what I'm going to say is not so true for these stars. But for the cases in which it's closer to the surface acoustically, okay, what would you use to detect that signature that you're saying, D02 or D01? And you understand why one would work and the other would not work?
I would use D02 because this is directly a function of the integral of the gradient of sound speed. D01, the thing is that the L=1 modes are not pure pressure modes.
Forget about that.
Yeah.
I imagine they are pure pressure modes. If they are sensitive to the core, then it's different. If there's the modes, the 0 and the 2 have very similar frequencies, right? If you have a glitch that is close to the surface, if you imagine the waves of the 0 and the 2 with very similar frequencies, starting from the surface with similar boundary conditions, they will see the outer layers in a very similar way, that their phase is going to be very similar. Okay, and so they'll get to the place of the switch with a similar phase. So they do not contain much information about the glitch. The D01s will include more information because they are out of phase, the 0 and the 1. The phase at which the wave gets to the position of the glitch is different. Okay? What I'm trying to say to you is that I think if you, and that's shown in the ratios in the paper of Rocks, where it shows that the ratio 0-2 do not sense the bottom of the convective region, while the 0-1s do, right? And you can go through the paper. It's not very important. What I'm trying to pass to you here is that these D0Ls, I think they can contain, if you explore them, they can give you more information about the core.
Because they differentially probe.
Because they differentially probe,
Yeah.
and the reason why, exactly, because you have cavities that differ, right? And so you subtract somehow the outer part, but differently depending on the combination of those you get. And if you had the L equals 3 together with the L equals 1, which was my original question, few pressure modes, then that would be combining that with the 0-2 would be the optimum, because the 0, like Stefan was saying, goes all the way down.
Yeah.
All quantities you have in your plots contain the 0. So all of them have that information. But if you have the 1-3, the 1-3 will not contain that information. And so if you subtract the 1-3 from the 0-2, you can actually probe the core. Okay. So just think about this for the future. Yeah. Thinking about exploring this a little bit more, because I think it's another way to go from the work that you did, and I'm very happy to do it, and I'm happy
But yeah, actually, I have
discuss the case.
Yeah, sure. We can discuss a lot more that.
Okay, now, Sure. Good, please. Try to be short. Short also in the answers, please. I know there is a lot of discussion to be done, but it's counted.
Thank you, Guillaume. I really enjoyed your presentation. So short questions, short answers. For the mass loss, I have a few questions about mass loss that you included in the models. First of all, why did you choose the values of these parameters? I mean, for Reimers, you choose 0.3. I've seen higher values used before. So why 0.3?
So this value is based on the recent works of Andreas Miglio, who show that to reproduce the mass loss integrated, so from the RGB up to the clump phase of all the open clusters, they recommended these mass loss parameters. So this choice is based on this image.
And the other one for broken or the AGB.
This is a more tricky question because I struggle to find typical values. So
you are not alone.
This is not only based on observations. This is also based on stellar models to reproduce mainly based on stellar models to reproduce the integrated mass loss from the clump phase. Yeah, I don't really remember about that, but this is based on stellar models, not on the observations.
I have a small question. When you mentioned your low mass AGB stars, your AGB clump stars, from 0.9 to 1.1, so mass is something like that, you mean the mass of these stars in the clump or the initial mass of your model?
Yeah, this is actually a very good question. This is the all I consider all what I mean by 0.9 or 1.2 solar mass is the actual mass, okay. The current mass, not the initial mass.
Okay.
So when I am averaging the location of the AGB bump from stellar models, I took it at the mass at the AGB bump and not at the initial.
So these stars have typically what mass at the beginning?
So for the more massive one, most simple, they do not lose a lot of mass. So the initial mass is basically the same as the final mass.
Yeah.
For the least massive stars, so around 0.9, they lose like 0.2 solar mass.
1.1.
Sorry.
1.1 is at the beginning.
No, 0.9 solar mass, and at the end 0.7.
Okay.
And it depends on the metallicity also.
Okay. Sure. So of course I'm going to go back to the problem of mixing that you mentioned. So you mentioned rotational mixing, and then you mentioned also that the core rotation rate goes as the inverse of reduced squares. Like the angular momentum, basically. That means basically that there's no shear developing in these stars. It's also reducing the shear because the star is increasing in radius. So my point is, you shouldn't have a lot of rotational mixing because shear is just not there enough. It's not there during the red giant phase, and it seems not to be there also for the AGB phase.
So for this case, in my models, I am only considering core rotation during the main sequence, not on the clump phase. In fact, well, this choice is not based on this assumption, but this is due to the fact that when I consider the core rotation from the main sequence up to the AGB, it did not really shift the location of the AGB. In fact, it does not shift a lot, considering either only on the main sequence or all the way through the AGB. So I only kept rotation on the main sequence.
Okay, but rotation in terms of mixing induced by rotation or just the centrifugal acceleration? Because there are two different effects. So you have both or just one?
It's mostly there are 6 instabilities that are considered in a diffusive approach for diffusivity of rotations, which is based on instabilities.
My point is, even if you keep rotation modeled in a realistic way, we don't expect a lot of mixing from rotational instabilities, right? Because they don't have a lot of shear. At least from the observational point of view, we don't see it there. So probably it will announce that rotation will do that. So a way also to check its mixing, where is in action and so on, is to look at surface abundances, how they evolve, and also the S process yields.
Yeah, so from my study, I noticed that at a specific threshold in the core rotation rate, with respect to the critical angular velocity, the decomposition from the core, so the hydrogen and the helium, starts diffusing in the envelope. So I think the limit was around 0.25 fraction of the critical angular velocity. But below, the effects are not visible, at least on the position of the AGB, but mostly also on the profile of the hydrogen and helium abundance, which is mostly above a critical value.
This effect of this extra mixing in the S process yields, if you looked at it?
No, not really, no.
It's an idea for the future. Might be interesting. You did a lot of things. One last question, short one. So we're trying to determine whether the location of the AGB bound, whether this is a good standard candle. And I have a bit of difficulty to find the usefulness of this new standard candle, in the sense of which object are you going to determine the distance using the standard cannon?
This is mostly the HB bump event that is used as standard cannon, not the stars themselves.
Sure. But for which object are you going to determine the distance using this method? The standard cannon. Because if it is in our galaxy, well, we have Gaia today, then it's very reduced, it's parallaxes. If it is other galaxies, can you really locate the luminosity of the comet in these galaxies or isolate themselves?
Well, for Kepler data, not really, because we don't have this seismic data for these stars,
exactly.
but actually, I don't have any answer for that.
Thank you. So before I think we talk to I have just 2 questions. So first, I appreciate the large introduction. I'm not especially so reading a lot of the rest. When we're doing observation, we talk a lot about the instrument, scope time, and you're doing computations. So did you have some problems to make a computation? Did you have limitations? Did you need more computational time? Was it a limit for your thesis to computer time?
The models, you mean?
The computer time, the CPU time.
So for this work, I have computed grids of models, so with several combinations of metallicity, mass, etc. So for that, I could not do it on the local machine. I had to,
Yes, but
get.
It's a matter of weeks or matter of months or matter of
Matter of weeks.
Because I remember I've done some computation in the past and we had to make the run during all the weekend or all the week for the results. And realizing that we made a mistake at the beginning. Okay.
But yeah, I computed several times, but it's mainly because it only lasts 1 week.
Because you said also that you had to avoid some computation because you have too many modules.
This is 2 different kinds of problems. For the stellar models themselves, I only need 1 week to compute one grid of stellar models with several masses and metallicities. For the modes, no, it requires really more time because we need for the most evolved giants at a very high luminosity stage, we need more like 100,000 millions of mesh points to resolve the mesh points. Check it with the team.
Okay, thank you. Last question. In your chapter 11, you talk about chemical enrichment of the galaxy. I see you have ages, you have distances. You also, for me, it's you talk about maybe sometimes gradients. And you talk about the different mixing, so different yields. Can you comment on that? Do you have some projects on that?
Okay, so this may be something I will investigate in my postdoc. So here, what I mean by the further investigation we can do with this work is that because we can constrain mixing processes in stellar interiors, it will impact the core composition, but also the composition of the envelope, which is directly in contact with the stellar environment through mass loss processes. And in this way, it can impact the chemical evolution of the galaxy. So what I mean by implication for galactic archaeology is following the evolution of the galaxy, particularly the chemicals, thanks to stellar nucleosynthesis and these mixed diffusive processes, stellar interiors, all they impact the chemical environment.
Okay, good, thank you. So now it's your turn.
So I've prepared my sentences in French, so. So the first thing I like to say is that it was really a pleasure to have Guillaume as a PhD student. Really fine, very pleasant to work with. Was a very fine mood, constant mood, very comfortable. Also, I would like to say that I was impressed by your work, the quantity of work and the reactivity in front of our questions, concerns, demands, etc. You came very rapidly with answers and to say. Well, I should not say too much because I must let some space to yes, so it was pleasant to work with you. Reading your mails at 7 a.m. when I began to work and realizing that they were sent at about 3 a.m. in the morning because we were very orthogonal with respect to working hours. So from the point of view of models, because it was my part, of course we didn't use César. We are working on the helium flash, but numerical is not so easy, and the system is not the only tool that cannot do that. So we decided to use LISA. And we decided not to use LISA as a black box. And here came difficulties. So because, how to say that? There were some impasses because we decided to go as good as possible. So we had some disappointments with the atmospheric boundary condition treatment, for instance, and it took a lot of time. And then we had surprises concerning, for example, the step overshoot, which is not treated as the usual way. Well, so Guillaume built grids, well, a week of calculations about it, and then, well, no, it's not good. You have to modify, understand better for this jungle of parameters. And I have found that you didn't, sorry. You didn't, yes, you didn't give up with that. A lot of courage with those grids. It's not so easy. So I have to congratulate you with that. And so I will let Benoît, I would say,
merci, Evelyne.
Bravo, Guillaume. And good luck for the future. I'm sure it will be, you will have many things to do, to explore.
So, Guillaume, it was a pleasure to work with Evelyne and with you. And it's clear that you now have skills in fields in mind, and it's really nice to see how you were efficient to do so. And efficiency was already presented by Evelyne, but I have the question. How can you be efficient since you don't drink coffee, you don't drink wine, you don't drink tea? I don't understand how you can be efficient, but you are. And you were efficient despite the COVID. Many PhD were delayed because of the COVID. In fact, you are an even-tempered guy, and of course, the period during COVID was not easy, but you managed to find the energy and the energy you already had just to work, and it was really appreciated. You have taught during your PhD, and your colleagues and your students always to be it's very good teacher. And it appears here in your presentation. Certainly, it's one of your one more of your skills that we appreciate. So I don't know what your future will be, but according to what you have seen, this future will be bright. Since you have really skills are able to study in this field of resilience, and the list of your prospects is give you work for the time. We were long. I will stop here. Thanks again, Guillaume.
Thank you, Guillaume. No, I forgot to add that in your manuscript, there are more than 500 references. This is quite impressive just to read them and understand them. On top of the work you've done. Okay, I think we leave for a while for the evaluation. And we'll come back as soon